Hi everybody, my name is Bruno Malet-Damour. I'm an associate professor at the PIMENT laboratory of the University of Rhode Island. My research and teaching are focused on the theme of building, its energy efficiency, and the multimodal perception of occupants. Bioclimatic architecture is one of them. I will be presenting this webinar on solar architectural design and the specific case of an island. Before starting, let's situate Réunion Island. Réunion Island is, with Mayotte, one of the only two French departments in the southern hemisphere, and more precisely in the Indian Ocean. Réunion Island is subject to a humid tropical climate with a strong solar deposit. Due to its very uneven relief, representative of its volcanic geology, Réunion Island is divided into about 40 microclimates. Designing on an island, such as Réunion, means having to meet performance objectives in a constrained context. Indeed, the tropical climate of the island and its multitude of microclimates force us to have a particular and sometimes mixed approach. At the same time, the island, like many other islands, suffers from its remoteness and its isolation from France. The economic and social context of Réunion Island is part of the constraints to be taken into account, as well as the level of abundance of resources. All these constraints will have to be perfectly used to become advantages to meet an objective of energy, to consume as little as possible, of comfort, to reach a comfort all year long without consuming energy, economic, by limiting the cost and the number of materials, and finally, by taking into account the life cycle of materials. This necessary optimization will make it possible to design buildings that are the most respectful of their environment and of the people who live there. Climate. The unprecedented climate change has and will have significant consequences in the world. Plus 6 degrees Celsius by 2100. In Réunion, it is plus 3 degrees Celsius by 2100. The island is subject to numerous cyclonic systems. The position of the intensity of this phenomena is changing over the years, always due to climate change and its many origins. Greenhouse gases, massive industrialization. The more time passes, the more Réunion Island will experience cyclonic episodes of higher intensity. As far as the sea level rise is concerned, the figure indicates that the island is at one of the highest rates, plus 5 mm per year. If this rate remains constant, which is not very probable, it means that by 2100, the sea level will have risen by almost 445 compared to 2011. About economic and social aspects. As the vast majority of building materials are imported, 380 million tons in Réunion in 2014, transportation represents a significant part of the costs, especially as they are heavy and bulky. But on site, another problem arises, that of storage. Indeed, the economy of the islands is faced with a common problem of land scarcity, which results in a lack of storage space, leading to an increase in commercial rents that are reflected in the price of materials. Imported building materials are more expensive to purchase in Réunion than in mainland France, by about 49%. Mechanically, a higher purchase price of material leads to a significant increase in the price of construction, insofar as the purchase of materials and their assembly constitute one of the most important items in the overall price of new construction. These costs harm access to the property as nearly 60% of the population lives below the poverty line. However, the high demand of new construction and renovation is consequential and will need to increase housing capacity by more than 170,000 units by 2035. And resources are also a scarce commodity. Indeed, UNESCO recognizes that the pitons, cirques, and ramparts of Réunion Island create a spectacular landscape and contribute to the conservation of the terrestrial biodiversity of the Mascarena Island. These areas are therefore protected, and the story continues. The park's charters must be revised every 10 years, which may lead to the extension of the boundaries of the protected area. The resource that we have on the island with abundance is solar deposit. Indeed, in overcast, we can reach nearly 80,000 lux. In a clear sky, we reach values up to 200,000 lux, when we know that for radiant activity, only 500 lux are necessary. The modern construction in method in Réunion, as in other islands, is based on the massive use of concrete. These construction methods use local alluvial resources. A local public organization, CESAR, insists on the fact that these material resources are to date mostly non-renewable. The challenge is to reconcile the economic development necessary to meet social challenges with national and European requirements for environmental preservation and ecological transition. It is necessary to build, but to build well. It is necessary to adapt the building to the individual by respecting the natural cycles of man and the climate. Let's talk about bioclimatism. The term bioclimatism was first used in 1960. The word has both Latin and Greek roots. Bios, from Greek, the life, means of living, resources, living together. Clima, from Latin, inclination of the celestial cap. In other words, land area determined by geographical factors, including weather condition, sunshine, air temperature, wind, precipitation, topography. We can therefore give as a definition of bioclimatism means of living with given resources in a given geographical and meteorological context. Be careful of modern bioclimatism, which is not really a modernization of vernacular architecture. Bioclimatic architecture exists in certain vernacular architectures, specific to a place, a time, or other. It is often based on ancient traditions resulting from an empirical experience of the environment at the crossroads of available materials and the search for a response to local climatic conditions. Indeed, architecture is an emergence of the climate, the soil, and the resources of the region where it develops, and it is based on an economy of means adapted to a balanced local development. Often, this research, fruit of 1,000-year-old evaluation, has given very original and efficient results in use until the generalization of fossil energies. For a real autonomy at the time of the energy decrease, the construction of the habitats should thus be again adapted to the natural condition of the place. Local natural materials, low energy consuming designs, even energy producing, artisanal, empowering, and emancipating technique of implementation. These are the foundations of vernacular architecture. However, vernacular construction is not only about using local traditions, but also about taking one's future into one's own hands and trying to free oneself from the laws of the construction market. The term vernacular also has a precise economic meaning. The building must be designed sustainably for a given climate to improve people's comfort. Sustainable because the climate will tend to change. The architecture will have to be efficient today and in 50 years. It is therefore necessary to understand the climate and the expectations of the occupants to design the architecture sustainably. Poor design will lead to climate dissatisfaction. The building will become energy intensive as people try to restore these satisfaction levels. The excess energy consumed by the building will again burden the climate. As the climate changes, the building can only become inefficient. Under these conditions, it is necessary to understand the climate. Let's take the example of the Réunion Island. What do we have as climatic solicitation? There are three main types of winds in Réunion Island. The trade winds, regular southeast winds, weak to moderate, seasonal. The breezes, regular phenomena, both in time and in the mode of circulation, and the form. In addition to the hydraulic aspects, it is necessary to take into account the solar exposure, symbolized by the solar path, as you can see in this picture. Réunion being in the southern hemisphere, to increase the solar exposure, it will be necessary to face north. If we focus on irradiation and temperature, we can see that the climate is tropical and humid on the coast and rather temperate in altitude. The diurnal and annual thermal amplitude for a given place of the island is very low, from 5 to 7 degrees Celsius. The temperature decreases with altitude. It drops about 0.6 degrees Celsius every 100 meters. Strong solicitations distributed on the territory indicate that it is necessary to adapt the architecture to the climate. Climatic architecture is not a new invention. It is simply a rediscovery of very old principles that were imbued with common sense, but that economic and energy facilities had ended up making all builders forget. Not having the means to oppose it, man has always in the past composed with the climate. He has observed the influence that were favorable to him and have produced a type of construction that is in many ways exemplary. Different strategies must be employed depending on the season of our climate. When the strategy is to cool the building, what is called summer comfort, 4 words of order: cool and protect, minimize and dissipate the heat input. For this, it will be necessary treatment of the building surrounding, natural ventilation for the building, limitation of internal heat gain, solar projection, optimization of thermal inertia. When the strategy is to heat the building, which is called winter comfort, 4 watchwords: capture, solar radiation, keeping, storing and distribute. For this, it will be necessary to optimize the capture of solar gain through the windows, maximize thermal insulation, drastically reduce thermal bridge, control ventilation and eliminate infiltration, and optimize thermal inertia. To achieve these objectives, we will study the technical solution according to the 3 aspects: environmental clause, solar design, and hydraulic design. There is not always much room for maneuver when sitting in a building, especially in urban areas. However, the principles governing the choice must be kept in mind. They are based on the most detailed knowledge possible of the characteristics of the seat, such as the level of variation in temperature, sunshine, and the time of fog or mist, or the masks near vegetation, urbanism, and far mountains, likely to reduce or increase the insulation of the building. The main parameter is the effective duration of insolation and therefore the effect of max. The building will be placed in a point of the ground reducing to the minimum or maximum the influence of the mask and will adopt an orientation full north maximizing the solar contribution or full south to minimize them, in the case of Réunion Island. In Réunion Island, the building should give priority to the main north and south facades, minimize the east and west gables. The orientation allows reducing the very important solar contribution for the east and west orientation. Avoid southwest orientation. The December sun is very intense at this time of the year. When sitting in the building, one should also try to orient oneself towards the winds that are beneficial of summer comfort, breeze. However, in urban centers, the wind direction is influenced by arteries, building, and the topography of the city. A first idea of the best location can obtain by evaluating the obstacles around the area to be built. Favor the thermal breezes and not the trade winds. Indeed, the trade winds do not blow in summer. Only thermal breezes prevail. They are perpendicular to the side, sea-land direction during the day and land-sea direction at the night. For the east and west zones, the main facades should be oriented northwest or southeast to configure solar protection and thermal breaks. In the upper part of the island, the main facades should be oriented north and east to benefit from the winter sun. In order not to lose the potential of solar heat gain in winter and to protect against it in summer, when deciduous trees in front of the facade exposed to the sun. In winter, this will lose their leaves and allow the sun's ray to enter. The evergreen vegetation masks allow protecting the building from cold winds and noise sources. The difference in temperature at 1.2 meters from the ground between an area without trees and over containing trees is equal to 0.7 degrees Celsius on average and can reach a maximum of 2 degrees Celsius depending on the importance of the shading areas. At night, there is generally no difference. Asphalt and concrete surface around the building to avoid causes increase heat gain and create a warm microclimate around the building. Solution: the finished ground around the building must be effectively protected from direct sunlight over a strip at least 3 meters wide. This is mandatory for ventilated facade. The nighttime temperature decreased by 0.3 degrees Celsius when the vegetation density increased by 10%. During the daytime, cooling is not always observed and depends on the type of vegetation encountered. A mature tree in a tree plantation can evaporate up to 450 liters of water per day, which cools at as much as 5 air conditioners running 20 hours per day. You can see in this picture the case of vernacular architecture. The vegetable proximity is frequent in Creole, Cuban, or Indonesian architecture. Now, let's look at the solar design of the building. The sun path corresponds to a trigonometric translation of the sun's position at an instant t. It allows to determine the exposure time of an element to dimension a solar projection. It is based on the calculation of its horizontal coordinates, the azimuth and solar altitude. The variability of the solar geometry is related to the true solar time, TSV, whose deviation from the Lagrange time can be determined according to the equation in the literature. These solar paths allow, among other things, to determine the solar exposure rate of a building by taking into account the masks. A solar mask is anybody that prevents the sun rays from reaching a surface that you want to sunlight. The distant makes are caused by relief, neighboring buildings, or vegetation. Tools are available to quantify the impact of this mask on the exposure time of the building. Consideration of the position of mask and solar exposure must be coupled with another strategy. A good distribution of the rooms is important. Here again, common sense will allow you to make a simple choice that favor energy aspects while respecting other constraints. In a winter strategy, for example, the southern in northern hemisphere and northern in southern hemisphere facade is a source of energy and light, and it is on this facade that the most frequent rooms will open up, as well as those where it should be most present to light. Generally, these are the bedrooms and living rooms, and even the kitchen in some cases. When the construction allows it, this room should be arranged from east to west to follow the path of the sun. Bedrooms to the east, wake up with the sun, no overheating in summer at the end of the day. Living room rather to the west or north. On the other hand, the rooms where the temperature is lower, those where one stays little, those which need less light will be placed on the south facade. These are the sanitary facilities: bathrooms, kitchens, storerooms, corridors, stairwells. This arrangement allows the entry of new air on the north facade and its extraction by rooms located on the south facade, which favors the distribution of it from north to south. The distribution of a dwelling with a veranda must be articulated around it. The principles described are the same, but we try to have as many rooms as possible open onto it. This facilitates the transfer of it from its place of production to its place of use. In a house, it is necessary to organize the surfaces according to the needs, according to whether it is necessary to protect oneself from the sun or not, or to bring natural light. In an office, it is simply necessary to dimension the glazing to support the natural light while bringing devices of solar protection of the summer. The organization of spaces can be considered: offices, relaxation room, meeting room. Partitional spaces into different zones allows for the creation of protected spaces and different thermal atmosphere better suited to the specific use. The veranda was used a lot in 19th century, whether it's individual houses or on a different scale in the large collective spaces such as covered passages or shopping malls. If the veranda is experiencing a revival today, it is because it can be used for a variety of purposes. The first of them is its character of boiler in winter comfort or shaded area in summer. The veranda is indeed a significant source of heat or coolness for the house. Being a buffer space, not heating or air conditioning, it is not permanently occupied and can therefore be the seat of temperature fluctuation much stronger than inside the house. This is why it can be fitted with a large protecting glazing surface without disadvantages. This function makes it a nomadic space occupied only a few years a day when the interior temperatures allow it. A veranda should never be heated with a heating system. This would increase the energy consumption of the house. The occupation of the veranda will necessarily be intermittent. This is precisely where it finds its second function, that of additional space in the house. This function is often the only one that occupants have identified the character of the boiler often escaping them. But this additional space has very particular characteristics linked to its nomadic character, but above all, it is a pleasant space, generally more pleasant than any other room in the house. Space is enveloped in a luminosity that only its great transparency of the outside can offer. The typology of verandas is rich, but in practice, their construction in social housing is limited to a few configurations. By schematizing, we can identify 4 types of verandas. In what? They are simply attached to the front of the housing. The solution is quite common, especially in rehabilitation, but does not have many advantages. It has the disadvantage of being very inefficient in terms of energy and of causing strong overheating in summer. It does little to promote heat transfer to the home. In corner support, it is a form of partial embedding of the veranda in the housing. This solution is intermediate between the wart and the total embedding. It has the advantage of better managing solar gain than the previous solution. A semi-recessed, this arrangement is often adopted because it allows a lateral opening of the veranda, increasing the field of vision from inside. But this is penalizing from an energetic point of view, so that the performance are close to those of the veranda with corner support. Recessed, the veranda is fully integrating into the house. It does not create a projection of the facade. It is by far the most efficient solution from an energy point of view because almost all of the heat trapped is transferred to the house thanks to the multiplication of the contact surfaces between the veranda and the house. It is also these large surfaces that, by maximizing the internal inertia of the veranda, ensure excellent comfort in all seasons with this solution. However, there are 2 variants, with or without glazing of the cover. The version with a glazed cover is even more efficient but not recommended due to the summer overheating it generates. If we had to establish a list of desirable choices, we would place first in the recessed veranda without a glazed roof, then the semi-recessed veranda, the veranda with corner support, and lastly, the verandas as a wart, which are not very recommended. Whatever solution is adopted, the problem of the veranda roof must be examined closely. All experience shows that glazing the cover systematically leads to overheating in summer. A veranda that is uncomfortable in summer will make its occupant forget all advantages and comfort it provides during the rest of the year. The risk of overheating should not be underestimated. The veranda is a key element in Creole architecture of Réunion and Mauritius. Within the different typology previously described as a wart in corner support for Mauritius, semi-recessed for Réunion Island, and another example in Réunion Island, recessed. The solar gains are concentrated during a few hours of the day, while the needs in heat and cooling are continuous. It is therefore necessary to store a part of this contribution, winter comfort, or reduce the effect in summer comfort, for summer comfort. The objective is not to ensure the total autonomy of housing, but only to contribute to reducing the heating or air conditioning load. Energy storage is based on thermal inertia of the building, capable of storing and then releasing heat. This inertia can be constituted by all the heavy elements located inside the heated or cooled volume. This includes walls, floors, furniture. The most suitable materials are dense materials with high specific heat, concrete, stone, brick. So the implementation of these masses must respect precise rules. The ratio of the surface of the exposed mass to the glass surface must have a minimum value. For this, we will avoid concentrating the inertia, and we will rather seek a large surface of exchange, even if it means reducing the thickness of the walls. Also, prefer interior walls, floors, walls, with a double exchange surface to exterior walls that have only one. The storage cycle implies the existence of variation in temperature of the walls and the ambient air. This is well accepted by the occupants, who find it rather pleasant. But this variation must not be too important, because they would increase the thermal losses and the discomfort. Thermal inertia also reduces the daily fluctuation of interior temperature, thus improving comfort, a phenomenon that everyone has already observed in the whole house. Finally, it should be remembered that the body is very sensitive to the temperature of the walls. In winter, the higher the temperature of the walls, the lower the temperature of the air, which is physiologically better. In this sense, thermal inertia is a great source of comfort. The position of the thermal masses is of particular importance. Climate-responsive design means positioning thermal mass when it is exposed to appropriate levels of passive summer cooling and solar heating in winter. A badly positioned mass heats up and radiates heat well into the night when external temperature have dropped. As a rule of thumb, avoid or limit thermal mass in upstairs sleeping areas. In climates with little or no heating requirement, low mass is generally the preferred option. Only the specific characteristic of materials for bioclimatic architecture will be discussed here. It is considered that the characteristics of thermal insulation are already well known to the project managers. In climatic architecture, we expect materials to allow both a good absorption of light rays, heat storage, a good speed of absorption and restitution of heat. To achieve this material must have certain specific characteristics as heat capacity. The higher the heat capacity, the more energy the material can store to raise its temperature by 1 degree. The higher the thermal capacity of the material, the smaller the temperature variation of the wall and the air. Generally speaking, the material with a high thermal capacity are also the heaviest: concrete, stone, brick. The protection of the roof is necessary. The roof transmits up to 2/3 of the heat transfer from the envelope to the interior of the building. One method of leaving solar protection on roofs is a green roof. Given the surfaces concerned, the greening of roofs is a major challenge for the recovery of biodiversity. Green roofs present various interests depending on the type of roof and the technique used. Creation of new habitats for fauna and flora, niches and shelters for birds and insects can be installed. Cooling of the air in the city, reduction of urban heat island, and filtration of volatile microparticles. Rainwater management, depending on the thickness of the substrate and the density of vegetation, water will infiltrate more or less quickly. Runoff water will also be limited. A 12 centimeter thin substrate can retain up to 90% of rainwater. Depending on the quality of the substrate and the percentage of the slope, the water will also undergo the first filtration. The vegetative roof can absorb up to 50% of the water falling on it. Thermal and sound insulation, when the thickness of the substrate greater than 10 cm and the height of the vegetation are sufficiently high. Thus, a green roof can reduce your energy consumption. And to finish, protection of the building materials. Sufficiently developed roof protect from UV, frost, and bad weather. Roof can see the lifespan of its waterproofing almost double. As for the walls, they should also be considered carefully. To reduce the interior temperature of the walls, increase the thickness of wall insulation and especially place the insulation outside, which will prevent the masonry from storing heat during the day. That will restore to the drilling eventually during the night. And two, ventilate the house at night. The important thermal inertia of the masonry will allow storing this nightly freshness to restore it during the day. The type of materials used for the roof or the walls is often linked to the availability of materials of the climate in force. In Martinique, in the high altitude, some buildings use rubber stone walls to increase the thermal inertia of the envelope. In the Philippines, the construction are sometimes mixed. Strong inertia on the first floor, use of stone, and light structure of the upper floor, use of wood. In addition to the notable interest in the weight of the construction, this also allows creating a continuity of inertia or regressive inertia between the ground, the first floor, and the upper floor. This is also the case of one of the examples in Réunion Island. Heavy construction, here you can see heavy construction on the first floor and light construction on the upper floor. Moreover, an architectural process is marked here by the transformation of raw resources. In the 60s, 70s, import materials were expensive and accessible only to a part of the population. The sheet metal used in cladding was rare and expensive. As a result, all barrels made of steel were recycled. This construction principle of low inertia is found in Seychelles, as you can see in this picture, with walls and roofs made of sheet metal. Mayotte still has the vernacular architecture at the time, using mulch and dried branches for roofing. For the materials constituting the inertia to absorb solar radiation or reflect it, their color must be correctly chosen. In greater comfort, the walls directly reached by the sun must be rather dark. Surfaces should, as far as possible, be bare. Avoid carpets and rugs in sunny areas. The color of the surfaces that are not reached by the sun can be any color. The solutions already exist. Simply take advantage of the expertise of the past, as you can see in this picture for Santorini Island. There are three main categories of solar protection: the fixed protection, the mobile protections, and the living protections. You can see donc some modern solar protection. Here, the adjustable sunshade, custom made by mobile sunshade, fixed sunshade, exterior blind, shutters, glazing with thermochromic glazing in the back of the picture, overhangs, awnings, finished overhang, and for the roof, passive or active roof, here with photovoltaic cellular, over roof just with a sheet metal and with green roof. In Creole architecture here in Réunion Island, the solar protection are often in the form of a fixed overhang. whether it is extended in picture 1 or limited to the side of the opening. The wooden shutters with a swinging cheek play the role of orientable, which reinforces the effect of solar protection. In Madagascar, the extent overhangs are often extensions of the roof and generally go around the building. The building is then a little open to the outside since this overhang goes down to the lower points. In Indonesia, and particularly at the island of Jakarta and Bali, the solar projection often plants either in the green roof with evolving vegetation and without substrate, or in a plant curtain offering coolness and protection. Let's move on the areolic design. Thin buildings are more advantageous than thick buildings. Thick buildings make it difficult to implement effective natural ventilation to the center of the building. Linear and narrow building fronts should be sought or access should be provided to an interior courtyard that can be used for natural drainage. The form of the building generally depends on the cultures. There's ways of doing things have evolved according to the climate and the material available. This is the basis of vernacular architecture. Here, to extend the limit of the study to the island, I have chosen to present some buildings from the African continent. The dome shape, as for the iglus, allows to keep the heat. It's the shape of a tagine, by the way, and to protect from cold winds. The photo below, when it keeps the rounded aspect put with more important porosity. In Madagascar, as you can see in the center of the slide, in some areas the building have a rectangular profile more slender than spread out. In Mayotte, the architectural form is close to the Creole culture, roof in two pans with an overall rectangular shape. And in India, the building is vault with a low rate opening. The openings will be located in taking into consideration the prevailing winds as well. The figure below illustrates in the plan the impact of different window opening designs on the air movement in a room, according to the prevailing winds, and with only the effect of wind is taken into account here. In the figure, the prevailing winds are represented by arrows. The green rows represent the airflow in the room, and the symbol plus or minus represent the areas of overpressure or depression. Whenever possible, the building should be located so that the natural air intakes are in the direction of the prevailing winds, overpressure zone. In this figure, you can see from poor situation to best situation, and in function of the position of the window. Earth-cooped concrete slabs on ground provide a heat sink where deep earth temperatures are favorable, at 3 meters deep or more, but should be avoided in climates where deep earth temperature contribute to heat gain. In these regions, use open vented floors with high levels of insulation to avoid heat gain. In regions where deep earth temperatures are lower, consider enclosing subwoofer areas to allow earth coupling to reduce temperature and therefore heat gains. Piles are generally appropriate in flood-prone areas. In this case, the inertia of the soil is not available, but from an aerobic standpoint, it is possible to improve the efficiency of the thermal draft. It is necessary, however, to specify that the constructions on piles are cut to structure with low inertia. obviously, to the weight of the structure. As is common throughout Southeast Asia or the Southwest Pacific, most Indonesian buildings are built on stilts, on piles. Houses on piles serve several purposes. They allow breezes to moderate hot tropical temperature. They raise housing above water and mud. They allow houses to be built on rivers and wetlands. They keep people, goods, and food away from moisture. They raise housing above malaria-carrying mosquitoes, and they reduce the risk of termites and microfungi. The structural system generally consists of posts, beams, and lintels that carry the load directly on the ground with wooden or bamboo walls that are non-bearing. In Indonesia, natural materials, wood, bamboo, trash, or fiber, form the roof. Hardwood is usually used for the poles and combination of soft and hardwood is used for non-load-bearing walls of the roof and is often made of wood or lighter thatch. The material for thatch can be coconut or sugar palm leaves and rice straw. The examples chosen are present here are Madagascar, here, India, Indonesia, and Sumatra. The shape of the roof influences the aerodynamic effect of the wind and thus the ratio of overpressure to underpressure that is created around the building. Scoops are devices integrated into the roof that reinforce ventilation by air intake or extraction. They allow the ventilation of central rooms. According to the work of CSTB, a technical group in France, the section of the vertical opening of a scoop must represent at least 20% of the vertical surface of the building envelope. Just like the general shape of the building, the shape of the roof is usually cultural. Here we see different roof shapes, from the very steep roof with openings in Indonesia, promoting thermal draft. The traditional houses in Indonesia respond to natural environmental conditions, especially the hot and humid monsoon climate of Indonesia. Moreover, the steeply pitched roof allows tropical rain to drain off quickly, and the large overhanging eaves keep water out of the house and provide shade. In hot, humid, low-lying coastal areas, pictures are right, houses may have many windows to provide good ventilation, and while in cooler, mountainous areas, houses often have a large roof and few windows, as you can see in picture left. Other roof forms are notable. There are, for example, the dome-shaped in Africa, on the very flat roof of Guadeloupe and Japan, which avoids the wind load, which in cyclonic conditions can be very harmful. Overhangs and outcrops are wind catchers. They create vortex zones that increase convection losses. In some constructions, the projections formed by the balconies can even be compared to the cooling fins of an engine process of a processor. Air stratification is a natural phenomenon whereby layers of air are successively superimposed according to their temperature. Above a height of 4 meters, the temperature increased by 1.5 degrees Celsius per meter. Lighter warm air is always at the top of the room while cold air stagnates at the floor level. It will best to choose a creeping ceiling instead of horizontal, particularly in tropical climate. Of course, this recommendation is valid for passive buildings, ventilated or heated naturally. In the case of the use of an air conditioner or heating, the volume to be heated-cooled would be too important, generating very high electrical consumption. With creeping ceiling, indeed, two consequences according to the need. In summer comfort, maximizing the ceiling height allows moving the hot zone away from the air. This architectural solution could be coupled with an air extractor. Moreover, be careful with the possible position of an air conditioner. The closer it is to the warm zone, the higher its concentration will be. In winter comfort, as the warm air is in the upper part of the room, the cool air is located in the living area of occupant. This is why you may feel cold when the room is well heated. By breaking the stratification of the air, you can save energy. To do this, you need to install an air destratifier. There are two main families of devices to destratify the air, the reversible ceiling fan and the air destratifier. Creating a wall that does not reach the ceiling allows to visually preserve the original volume of space and also to let light pass on both sides of the partition. However, this method does not isolate the two spaces from each other in terms of sound and smell. For this purpose, it is possible to glaze the part between the wall and the ceiling. The interior walls do not reach the ceiling, room separation, or within the same room. We can find the view breaker function. For advantages, cross ventilation for thermal comfort, additional light and better distribution for visual comfort, and about the disadvantages, sound transmission, acoustic comfort, and olfactory nuisance for olfactory comfort. Some remarks can be made. Prefer this construction method for rooms with specific use, kitchen, living room, dining room, and avoid for bedrooms and bathrooms. Creole architecture uses this construction method. If this arrangement can cause acoustic problems or more simply of intimacy, they are very handicapped for thermal comfort. The rooms have high ceilings and the building is easily ventilated naturally. On the left, you have the example of a building from the 60s in Réunion Island. On the right, an update version in this process. The walls of the same room do not reach the ceiling. This serves as a screen without obstruction, restricting the air circulation. In this case, we consider that the room does not have a problem with noise pollution. All at the world, natural ventilation for summer comfort was forgotten, with the profit of the active systems of cooling like air conditioning. The air renewal rates are much higher, above 10 volumes per hour. Only natural ventilation allows us to reach these flow rates. There are three different ways to achieve this ventilation for summer comfort. Cooling by direct ventilation, when the premises are occupied and when the outside temperature is cooler than the inside temperature. In the residential sector, this is the case for the ventilation of rooms during hot summer night. Cooling by delayed overventilation with a time lag, commonly called night overventilation, consists in getting the coolness at night and storing it in the available inertia of the structure to benefit from it by remission the following day. And cooling by air movement. In this case, the aim is to accelerate the the evapotranspiration of the skin and elimination of the skin's wetness. There are four different ways to maximize the natural ventilation. The single direction natural ventilation, if there is only one opening on the room, an air movement is created by the double effect of the outside wind pressure and the temperature difference between the inside and the outside. This creates overpressure in the lower part of the window and depression in the upper part. For the same wind speed, this motor is 5 to 6 times weaker than that across ventilation. Natural ventilation by thermal draft. The main engine of the air movement can also be the thermal draft, the pressure difference created by an altitude gradient between the air inlet and outlet and a temperature delta between the inside and the outside. This is also known as the stack effect, as it is often achieved by raising the air in a duct. The greater the height and the higher the temperature of indoor air compared to the outdoor air, the more the operation of the thermal draft engine is optimized. Natural cross ventilation. The pressure difference between two facades due to wind and differentiated sunlight in the main driver of indoor airflow. Of all the natural ventilation motors, the effect of the wind on throughout the roof is by far the most efficient, several tenths of volumes per hour for wind speeds about 1 meter per second. Assist and controlled natural ventilation, ACNV. The randomness of the climate is a main drawback of natural ventilation. It is thus a question of compensating for this weakness by reinforcing the system with natural devices, allowing to increase or to control the flows. At the entrance, it can be the degree of opening of the window or the adapted self-regulating vents. At the outlet, one can imagine registers controlled by the airspeed in the chimney, the wind by venturi effect or by a static fan, the sun which artificially superheats the air in the duct. At the technological level, what we generally have is a ventilation grid in the front frame or sash equipment with clamps, and on the roof, ventilation skylight, opening in the vaults, opening frames in skylight, railings, and wind tower. Wind tower, the principle is the turrets are composed of a fixed part onshore in a concrete slab and two mobile parts. A movable part with a van equipped with a hole is oriented towards the wind to create an overpressure, improving the draft. To further increase the thermal draft, glazing is added at the foot of the turret to increase the temperature and the outlet of the extraction ducts, and thus favor the draft in the form of a solar chimney. Natural ventilation control solution for roof or facade openings. We can use the opening of grille, frame, skylight, can be motorized and automated with sensors and control units, depending on the indoor and outdoor temperature difference, rain and wind, concentration of the gases indoor. There are many examples for architecture using the thermal draft and cross ventilation. Here on the left, we see a school located in Bali. In addition to benefiting from an open and luminous building, the siphon effect, draft effect, guarantees a convective phenomenon, ensuring a notable thermal comfort. The holes in the roof are also noted in the architecture of Guyana, Bali, Africa, and or even in the upper part of the vertical walls, as in the case of India. About porosity. Porosity It seems that the capacity of a wall to be crossed by the airflows is characteristic by this porosity. This one is one of the determining factors of the hydraulic sweep of the interior spaces. So regulation sets levels of porosity to be respected to ensure sufficient ventilation. We can give some example about porosity. Porosity is often related to the climate and the type of materials used. The continental climate, as in some areas of Africa, will make the porosity of the building will be low to maintain the heat. Tropical areas will seek to evacuate the heat stored by the walls by maximizing the openings, as we can see in the following cases of Réunion Island or you see over here, and Comoros. If natural ventilation alone is not sufficient, it is necessary to energize the airflows inside to more effectively evacuate heat loads and create a draft on individuals. Fans increase fluid circulation, which results in physiological cooling. They can be used to supplement insufficient natural ventilation. The larger the blade, diameter up to 1.2 meters, the more efficient the fans. Here are two examples of modern architecture by the hydraulic principles developed in the previous section. First example, the Saint-Joseph Media Library is the first media library on Réunion Island without air conditioning. An advanced bioclimatic design associated with natural ventilation and cooling allows the realization of a low-energy building. Cross ventilation, regulated by louvers, have been favored in all buildings whenever there is a little wind. And for periods of low wind, a central depression well in the main building provides an additional motor that represents the thermal draft, as you can see in this picture. Systematic air blowers complete the system in case of strong heat. The surroundings of the media library are heavily vegetated to control the phenomenon of the micro-heat island. Sustainable materials are used: wooden framework, wooden shingles, and masonry in basalt stones from Réunion. The second example, then, the rehabilitation of a teaching building at the university campus of Le Tampon in Réunion Island. The challenge was to transform a non-traversing building into a naturally ventilated building without the use of air conditioning. Initially, the premises were poorly ventilated and insulated. There were problems of humidity and condensation and the lack of light inside and on the contrary a glare outside depending on the time of the day, overhunting in summer and then cold in winter, and finally defective acoustic. To overcome all this problem, the building was thermally insulated. Multiple depression wells were positioned at the level of the circulation to create natural ventilation optimized by thermal draft, while allowing to maximize the uniformity of the lighting in the building. The surroundings were also treated by vegetation to create a microclimate beneficial to summer comfort. Vernacular architecture is the most efficient carbon footprints, LCA, energy performance, comfort, because it has taken the time to define a building strategy in line with the climate and resources. Modern bioclimatic architecture includes import materials based on strategy from elsewhere. If the thermal performance is good, the environmental impact of the import is not zero. There is a multitude of islands, all with different climatic, societal, and economic problems, therefore a multitude of techniques to study, adapt, and use. With this in mind, this year we start a research project called Arche, with aims to identify construction methods from the past or elsewhere to respond to local societal problems, associate to acclimate the most efficient architecture with a consideration of the effect of climate change, to respond ecologically to all or part of the housing needs, limit imports or reduce travel by identifying local or nearby resources, example neighboring island, and influence future regulation of the use of methods proposed and identified in this project by creating a reference system. Thank you for listening and for your interest in this webinar. If you have any question, I'm of course available and can be reached at my email address listed below or my LinkedIn profile. Don't forget, the act of building must reflect your principle and your soul, because the choices you make will have a consequence on our future. Thank you so much.